Before getting into details about cement chemistry, we first need to talk about cement. How is cement made? First, we need some raw materials, limestone and clays. At this stage, if you mix them with water, nothing happens. The materials don't react. What we need to get started is a little warm-up. Heat, some heat, a lot of heat. 1450 degrees Celsius to be exact. This causes the calcium from the limestone to combine with the silicon from the clays. This forms, mainly, calcium silicates.
And releases a bit of CO2.
Now that they are warmed up, if you mix them with water, they will react. Cement is a magical material. It is essentially the most practical way to make artificial rock of any shape, like homes, bridges, tunnels, and Christmas trees. It is also an excellent shield in times of war, to protect people from nuclear radiation, and against Mother Nature. It also helps us harvest energy. We've been talking about cement, but we really should have been talking about concrete, a perfect mix of aggregates, sand, and the glue, cement and water. You may ask, why do we use aggregates in concrete? Well, the main reason is economical. One bag of cement costs the same as 150 kilograms of aggregates. Now the question is, how does cement harden with water? Well, the cement grains dissolve and release the calcium and silicon ions into the surrounding water. These ions will form needles at the surface of the grains and platelet-shaped crystals. They begin to glue the components together and fill the space between the grains, using up the cement and water. The material is now solid. Strength develops quickly at first and slows down over time. This can be modeled using an exponential function. In fact, the formation of crystals and needles, unlike other materials, slows down very rapidly. This could correlate with the point in time where most surfaces are completely covered with needles. The exact atomic structure inside the needles is still the subject of debate between cement scientists. It does not show a well-defined crystal structure, but rather a nanocrystalline region where short-range order exists. The features are somehow similar to the 14 angstrom tubermorite mineral made of calcium oxide backbone layers, flanked by silicate tetrahedra on both sides, and containing significant amounts of water in the interlayer regions. However, in cements, more atoms join the party. The chemical composition of the needles is variable because the atomic structure may be full of defects. The calcium to silica ratio can in fact vary between 0.83 and 2. The water content ranges 1 to 6 molecules per silica. This might depend on temperature, the amount of water, the presence of others like supplementary cementitious materials. The reaction of cement is in fact a very complex physical-chemical process involving many different chemical species which combine together very fast, different hydrates, heat release, volume changes, high pH, surface charge effects, structural water, different aluminosilicate chain lengths, different density, thermodynamic equilibrium. You can see what challenge it is to cement all this knowledge together into something concrete. This would be the topic for hundreds of other Minute Cement. And as always,
Thanks for watching.